Hello everyone, welcome to our channel Code with Sunny, and in this video I am going to talk about number theoretic functions, which is the one of the video of Algebra Fundamentals required for competitive programming. Okay, so in the previous videos we have talked about binary exponentiation, Euclidean algorithm for finding greatest common divisor, and also the C of Eratosthenes algorithm. Okay, so in this video I am going to talk about Euler's Totient function and the number of divisors and how to calculate sum of divisors related to that. Okay, so let's head over to the Euler's Totient function, which is also called phi function. Okay, so before proceeding further, one doubt that arises in your mind: what is Euler's Totient function, which is obvious, and why we are going to study and understand this in detail. Okay, so the very frequent answer to this question is that sometimes in some of the problems that we are going to encounter, like we are going to face certain situation that needs to have the prerequisite knowledge of this Euler's Totient function, so that we can easily solve that problem efficiently. Okay, so for now, if you're not going to understand that certain criterias, no need to worry about. I am going to explain the practice problems along with that. Okay, so for convenience. Okay, so for now, let's head over to this Euler's Totient function and understand what is the actual algorithm behind this. Okay, so let's move further. So what does this function is going to do? This function is going to basically counts the number of integers in the range 1 to n, both inclusive, which are going to be coprime to n. Okay, now so let's understand this statement basically in some simpler words. Okay, so suppose we have been given integer like 10, then we need to find the number of integers from 1 to, and it goes up to like 10, that are going to be co-prime to this number 10. Okay, note that I am going to include the bounds of the this range also. Now you can easily claim that we can use some brute force, that is, you can just iterate from 1 to 10 and find out the if for the certain elements like GCD of a comma b is going to be 1, where b is going to be fixed, that is 10, and a is going to vary from 1 to 10. If GCD of some particular pair is coming out to be 1, our answer should be incremented by 1. Now this is basically the brute force, but in cases like sometimes we are going to encounter like q queries, like q queries should be given to us, and q is going to vary up to 10 power 5, and each time we have been like the number n is going to be like very large, like 10 power 4 and 10 power 5, or any of the numbers like very large number. So if we are going to ask some question to yourself, like can we perform this like brute force for every number or for every query that is given to us, then it is obvious that we are going to encounter TLE verdict in case of some strict time limit question. Okay, so we need to have some efficient algorithm to find out this number of integers in the range 1 to 10, which are going to be co-prime to this number 10. Now this number 10 here I am fixing, but you can have any number n that you need to calculate it about. So we have an efficient function, this is called ETF, which is also in expandable form called the Euler's Totient function, and in short form you can also call it as phi function. Okay, so let's head over further. Okay, now you can see I have taken some values of phi, and for some positive integers you can easily see from 1 to 10 that the number 10 is has the value 4, that is phi of 10 is coming out to be 4. You can easily see phi of 10 is coming out to be 4, that is this value. Phi of 10 is coming out to be 4, and the reason behind this is, you can see what are the numbers which are going to be co-prime to this number 10, that is GCD of a comma 10 is coming out to be 1, where a belongs to 1 to 10 both inclusive. You can see the number should come out to be 1, 3, and you can say 7 and 9. These are the four numbers. If you take the GCD of these numbers with 10, it will come out to be 1. So the what are the total count of this number? The total count of this number is coming out to be 4. So you can easily claim that Euler's Totient function value at the number equal to 10 will be 4. Okay. So this is the basic example. You can understand and interpret with that. Okay. Now comes the basic properties related to that. Then we are going to head over to the implementation and find out the best possible efficient solution to this Euler's Totient function. Okay, so for now, let's read out the properties. Okay, so the very first property is if P is going to be prime number, then GCD of P comma Q is 1 for all Q that belongs to 1 to P, where there is an opening bracket at P. So we have the following relation, that is phi of P will be P minus 1. We can write directly, that is Euler's Totient function at the value equal to P, where P is going to be a prime number, can be written as phi P equals P minus 1. So how this is going to come and how we can write it directly, let's understand that. Okay, now you can see if my P is going to be something like prime number, let's assume, for with let's understand this with the example, that is let's say we are going to have P equals 11. Then you can see what are the factors of this P. The factors of this P is going to be the 1 and the number itself. So if there are only two factors of this P, that is 1 and the number itself, then we can easily claim that if for this 1 we have the GCD of 1 and 11 as 1, and for this one GCD of this 11 and 11 will also always coming out to be 11. That is the number to the number itself, GCD of n comma n will always come out to be n. Now you can see if there are no more divisors of this P in the range 1 to 11, we can easily see the total number of count, that is count of integers that are going to be co-prime with this number n will coming out to be P minus 1. That is there are P integers in the range 1 to 11, you can see 1 to 11 there are 11 integers, and if only 11, that is GCD of 11 and 11 will always come out to be the number itself, that is 11. So for all the remaining numbers, because all the remaining numbers are not going to be a factor of this P, then we can easily claim that GCD of this, that is, oh sorry, okay, so that is ETF Euler's Totient function value at this 11 will always come out to be this 10. That is, if a number is going to be a prime number, then my value will always come out to be P minus 1. That is ETF of the value of P. Okay, so now let's move on to the next property. So my next property says if P is going to be a prime number, that is you can see here, if P is going to be a prime number and K is going to be greater than or equal to 1, then there are exactly P raised to the power K divided by P numbers between 1 and P power K that are going to be divisible by P. Okay, so we can easily write what are the number of integers in the range 1 to P power K that are going to be co-prime with the P power K, that is GCD of this number I and P power K should be coming out to be 1. So we can write it directly as this value. So that is phi of P power K equals P power K minus P power K minus 1. Okay, so how this relation came? So let's understand this one also with the help of example. Now let's say we have P as prime number and let's say we have P as 7. Now you can see, let's say we can also assume that K is going to be 2, that is K should be greater than or equal to 1. Now you can easily see P power K will be coming out to be 7 square, which is coming out to be 49. Now we need to find what are the number of integers in the range 1 to 49 that are going to be co-prime with this value 49. Okay, that is n. Now you can easily see that is GCD of this number I, which is going to vary from 1 to 49, and this 49 should come up to 1, and we need to count the number of integers for in the range 1 to 49. You can easily see if my number P is going to be a prime number, we can just easily say that what are the multiples of this prime number P, which is coming out to be 7, 14, 29, 21, 28 and 20, or okay, we have next number as 35 and it goes up to 42 and 49. Okay, now you can see these are the multiples of this prime number P, and if for these multiples, if you calculate this GCD, you can easily see GCD will always come out to be the prime number p, that is greatest common divisor. So for all the numbers we can easily say if p is going to be a prime number, then the number of integers in the range of 1 to p power k, where k should be like greater than or equal to 1, we can easily answer this like p power k will be the total numbers, and we need to subtract those numbers whose GCD is going to be not equal to 1. So for all these numbers, like multiple of these numbers, multiple of this prime number p, and there are how many multiples that is going to exist between 1 and p power k. You can easily see p power k divided by p, which is coming out to be p power k minus 1. So there are p power k minus p power k minus 1 numbers in the range 1 to p power k, which is going to be co-prime with the number p power k, where p is going to be a prime number and k should be an integer greater than or equal to 1. You can easily see. Okay, so we have this short relation which is going to be very much useful later on. Okay, I'm going to explain that also. So for now let's move further. Okay, so you can see I have something like okay. Okay, now my next property is if A and B are going to be co-prime, then phi AB equals phi A minus phi B. Okay, so this is going to be very much useful here to calculate the Euler's Totient function efficiently for any number. So this relation comes with the help of Chinese remainder theorem, and for now I'm going to skip this part and I'm going to explain this in my later of the videos regarding Chinese remainder theorem. So for now you can just memorize this relation, that is Euler's Totient function of two numbers, that is which are going to be like in multiple, that like a into b, where a and b are going to be co-prime, that is phi ab equals phi a into phi b. Okay, so let's move further to analyze the simplified form of this phi n. Okay. Okay, so here you can see I have done some simplified form of this phi of n, where n is going to be an any positive integer. How we are going to calculate that value, that is Euler's Totient function at the value n efficiently. Okay, so you can see I have a simplified relation phi of n equals n into 1 minus 1 upon p1 into 1 minus 1 upon p2, and it goes up to 1 minus 1 upon pk, that is k integers p1 p2 pk are the prime factors of this number n. Okay, so how this relation came? Okay, so let's understand how we are going to get this relation efficiently. Okay, so let's move further. So in one of the third properties that I have already mentioned is that is you can see phi. Okay, so I'm going to write it clearly. Phi of some number a into b can be written as phi a into phi b, where a and b are the co-prime numbers, okay, with respect to each other. Now, okay, any number n, that is any number n which is given to us, can be written as some, like if we are going to prime factorize this number n, it can be written as p1 power a1 into like p2 is the second prime factor and it comes exactly a2 times into, and it goes up to like pk power ak, and it is like similar to, suppose we are going to prime factorize this number 12, it will come exactly like 2 square into 3 power 1. This is basically the prime factor of this number 12. Okay, so I'm not going to just I'm not interested in like finding only the prime factors. Okay, now you can easily see I'm going to just make this relation much more simpler with the help of this properties. Okay, now we have to find what is the value of this phi n. Okay, so let's take phi of n. So if you are going to find the phi of n, it should be like using this property, phi of ab can be written as phi of a into phi of b. Now you can easily see I can write it as phi of like p1 power a1, and similarly into phi of p2 power a2, and it goes on up to phi of like pk power ak. We can write it simply as like that. Okay, now we can also expand this term phi of p1 power a1 and phi of p2 power a2 and phi of pk power ak with the help of second property. And what is that second property? If you have forgotten for now, you can easily see phi of p power k can be written as p power k minus p power k minus 1, where p is the prime factor, or you can say prime number. And in case of prime factorization, p1, p2 and pk are already the prime factors, okay, which is actually a prime number. So we can easily write phi of p1 power a1 can be written as p1 power a1 minus, it should be like p1 power a1 minus 1. And similarly I can write p2 power a2 subtracted by p2 power a2 minus 1, and it should go on for each prime factor. Okay, so let's simplify this statement. Okay, so I'm just going to just erase this stuff, and I'm going to explain in a little bit detail. Okay, so I have already derived this relation and I need to proceed further. Okay, so I'm going to just write p1 power a1 minus p1 power a1 minus 1, and it should be multiplied by p2 power a2 minus p2 power a2 minus 1. So for now I am going to write only these two terms, and let's take p1 power a1 and p2 power a2 common from this. If I am going to do this, it should be like p1 power a1 into 1 minus 1 upon, you can say p1. Again you can see, if I am going to take p2 power a2 common from this second term, you can easily see I have the term like 1 minus 1 upon p2. And it should be similar to, like, for the next of the statements I have been encountering the terms like multiplied by p3 power a3, and it goes up to like 1 minus 1 upon p3. Okay, so for the last prime factor I have the elements like pk power ak multiplied by 1 minus 1 upon pk. Okay, so one thing that I have already mentioned over here, that any number n can be represented as p1 power a1 and p2 power a2, and it goes up to pk power ak. Now you can easily see there is a term common coming out from this p1 power a1 and p2 power a2, and similarly up to p3 power a3 and up to pk power ak. So I can just take this these terms as common and make some statements much more clearer. Okay, so how I'm going to do that? So I'm recommend to watch this carefully. It should be like p1 power a1 will club with p2 power a2, and it is in multiplication. So you can write this as number n, and which is going to be multiplied by the all the prime factors terms like 1 minus 1 upon p1 into 1 minus 1 upon p2. If there are k prime factors, k distinct prime factors, I can write it as like okay, so here should be, it should be like p2. Okay, so for now I'm going to write it as p2, and it should goes up to like 1 minus 1 upon p power k. So this is the simplified term of calculating phi of n, and this is going to be much more efficient. We cannot simplify this statement, this equation that I have got to any more extent. Okay, so phi of n, it should be like this equation. Okay, so in the simplified form, as I've already stated, you can see like phi of n, we can calculate it as n into 1 minus 1 upon p1 into 1 minus 1 upon p2 into 1 minus 1 upon p3, and it goes up to 1 minus 1 upon pk, where p1, p2 and p3 and it goes up to p power k are the prime factors of the n. And you can also see I've got this statement which is exactly equal to this simplified form of this phi of n. Okay, so now comes the main role. And what is that main role? To find out the best implementation, that is, as I've already said, I'm going to just provide two implementations related to this problem, related to this algorithm: implementation in O of square root of n, and implementation in Euler's Totient function from 1 to n in O of n log of n. That is for all the numbers in the range 1 to n. Okay, so let's head over to the first implementation. Okay, that is going to find Euler's Totient function for a particular number n in O of square root of n time. Okay. Okay, so here is the implementation of square root of n time. Now you can see I have initialized my answer as n. Now this is very much important here. Also you can understand that this implementation is going to be fixed for a particular number. Okay, that is if I have been given n as let's say 12, I need to find what is the ETF value related to the number n equals 12. Okay, so this is going to work for a particular number. So I am going to initialize my answer with n, and this the reason behind that is you can see the coefficient for all this 1 minus p1 and 1 minus p2 will be n. I need to start with this n so that after getting a particular prime factor my value should be changed to n minus n upon this p1, and you can see this value is always coming out to be integer because n by p1 is integer and n minus some integer will always be an integer, and let's say it is as x, then my next value when I am going to encounter as p2 as prime factor, my value will change to x minus x upon this p2, and similar to that up to pk. Okay, so let's move further to find also the best implementation to that. So the reason is very simple. I'm going to just factorize my number n into its prime factors. Why I'm going to deal with the prime factors? The reason is again very simple. You can see p1, p2 and pk are the prime factors to this number n. So I need to find the prime factor of this number n so as to calculate this value n into 1 minus 1 upon p1 into 1 minus 1 upon p2, and it goes up to 1 minus 1 upon pk. Okay, so just I'm going to prime factorize in O of square root of n time, and whenever we found a prime factor related to the number n, I'm going to just apply the operation answer equals answer minus answer divided by this I, and the term is similar to this term. You can see my answer is already stored, and I need to perform this operation answer minus answer divided by that prime factor. Okay, so let's head over to another implementation, that is Euler's Totient from 1 to n in O of n log of n time. Okay, now this implementation is quite similar to the sieve of Eratosthenes algorithm. Okay, if you are going to understand that sieve algorithm, then it will be much easier to understand this one. Okay, now you can see I have this array, or you can say a vector of n plus 1 size, where we need to calculate for all the numbers in the range 1 to n. Suppose we have been given 12 as the number, we need to find the ETF values for all the numbers in the range 1 to 12. And how we are going to find that efficiently? You can also find that in the, like, iterate from O of n to, or like 1 to n, and in for every number I in the range 1 to 12, just find the ETF value in O of square root of n time. Then the time complexity will be like O of n into square root of n, and in case like n is going to vary up to 10 power 6, this will give us a TLE verdict. So we need to find an efficient solution to that. Okay, so I have and here the solution, which is quite similar to of sieve, whose runtime is quite similar to that of sieve. Okay, so you can see I have initialized my 5 values, that is phi of 5 with I, and the reason is very simple, that in the previous case I have just initialized for a particular answer with the number itself, and similar to that I am going to do that here. Okay, now you can see in case of sieve algorithm, whenever we find any prime factor, I am going to just mark all its multiple as composite, which is going to be denoted at false. Okay, now here is the simple case. When I am going to just encounter some prime number p1, I am going to just perform the operation to all the multiples of this p1, that is the phi of j, where j is the multiple of this p1. Okay, so phi of j will be changed to phi of j minus phi of j divided by the number I, where I is the prime factor of this number n. You can see whenever I found a prime factor for a particular number n, then we need to perform this operation, that is that number, that value into 1 minus 1 upon this prime factor. Okay, so why not, whenever we found a prime factor, just do that for every multiple of this prime factor and change that value to this value. Okay, so we are going to do that efficiently in like sieve of Pareto-Stein's algorithm. So you can see that I have the implementation quite similar to that of sieve. Just start from I equal to 2 and it goes up to I less than equal to n, and whenever we find phi of I equals I, it means that we have found a prime factor. Okay, so just iterate for its multiples. Note that I am talking about multiples, not the proper multiples. Okay, so that's why I'm going to iterate for j equals I and j less than equals to and j plus equals to I, and change the value of phi of j equals phi of j minus phi of j by I. For the value, for the number corresponding to j, I will be the prime factor of this number j. Okay, so this was the implementation. That is for all we need to find for all the numbers the ETF values in the range 1 to n. Then we can use this method to find out in O of log of n, that is O of n log of n time. Okay, so let's head over to the practice problems related to that. So one of the my favorite practice problems regarding Euler's Totient function is, you can see, spoj of LCM sum. Okay, and the link is going to be a clickable, so you can fetch these questions and practice that. So I have mentioned three problems. Okay, now let's head over to the some more number theoretic functions like calculating the number of divisors and the sum of divisors. Okay, so let's move further. Okay, so let's talk about number of divisors. Okay, now you can easily see any number n can be represented into its prime factors like p1 power a1, p2 power a2, and it goes up to pk power ak, where there will be k distinct prime factors of this number n. Okay, now you can easily see p1 power a1, like if p1 is the prime factor of this number n, like it is also factor of this number n, then p1 power 0 will be a factor, p1 power 1 will be a factor, and p1 power 2 will be a factor of this number n, and it goes up to like p1 power ak. You can easily see if starting with 0 up to a1, we will have a1 plus 1 choices for choosing this number, by that is like for choosing this first term. Okay, and similarly for like p2 power a2, it will be like you can choose p2 power 0 or p2 power 1 or p2 square, p2 cube, and it goes up to like p2 power a2, and again there will be a2 plus 1 choices for choosing this number. So overall, for finding the number of divisors of this number n, what should be like the answer for this question? It should be like finding the total number of choices for choosing the divisors. It should be like a1 plus 1 into a2 plus 2, sorry, a2 plus 1 into a3 plus 1 into a4 plus 1, and it goes up to like ak plus 1, where there will be k distinct prime factors of this number n. Okay, so you can easily see now for the number of divisors, if a particular number pi appears ai times, then we have ai plus 1 choices to choose for this prime factor. So for all prime factors, we can generalize the above statement such that number of divisors will be given by a1 plus 1 into a2 plus 1 into ak plus 1. It goes up to ak plus 1. Okay, so this is basically the formula for the number of divisors. Okay, so let's talk about some of the divisors for a given number n. So if we have been given a number n and we need to find what should be the sum of the divisors of this number n, so you can easily see some of the divisors of this n is given by this formula that I have written over there. Okay, so but how this formula came, let's understand that also. Okay, you can see n can be represented as p1 power a1 into p2 power a2, and for now I'm going to just limit this as only of two terms. You can generalize this for any n terms later on. Okay, now you can see I have this factor have like a1 plus 1 choices, so I can write this as p1 power 0, which will also be a divisor of this number n, and p1 power 1 will also be a divisor of this number n, and p1 square will also be a divisor of this number n, and it goes up to like p1 power a1, which will also be a divisor of this number n. And if I need to find the sum of the divisors, I need to add up all this amount, and if you focus on this addition, you should find that it is nothing but a geometric progression with common difference, or okay, common ratio, you can say common ratio as p1. Okay, so I can write this sum as 1 into my common ratio as P1 power number of terms A1 plus 1 minus 1 upon this common ratio minus 1. Okay, and if I have calculated for this term, I need to calculate for this another term like a P2 power A2, and you can generalize this for all of the terms. Okay, it doesn't matter. For now I'm just taking only these two terms. You can write it as P2 power A2 plus 1 minus 1 upon this P2 minus 1. Okay, and for k distinct prime factors you can write it as for P power k. Okay, similar to like this. Okay, so this is the basically sum of the divisors formula, so you need to memorize this for convenience. Okay, so here is the actually the end of this number theoretic functions, and for related to number of divisors and sum of the divisors I have mentioned two practice problems, spoj div sum and spoj div sum 2. This is basically the, if you need to have more focus on these topics you need to practice these problems. Okay, so if you have any doubts related to number theoretic functions, Euler's Totient functions and the number of divisors and some of the divisors, let me know in the comment section of the video, and I will ask the viewers to like this video, share this video, and also join the Telegram channel mentioned in the description section of the video, and do subscribe to our YouTube channel for latest updates. Thank you for watching this video.